Imagine a life where you never needed to close your eyes. Roughly 1/3 of an average human life is spent unconscious. Bypassing that biological mandate has been an enduring fantasy for centuries, often fueled by people claiming to have achieved it. Take Albert Herpin, an American born in the late 19th century. He was famous for allegedly not sleeping a wink for over a decade, reportedly spending his nights simply sitting in a rocking chair, reading. Or consider Paul Kern. Shot in the frontal lobe while fighting as a Hungarian soldier in World War I, Kern supposedly lost the ability to sleep entirely after the bullet was extracted, living in absolute wakefulness until his death decades later. The phenomenon extends to the modern era. In rural Vietnam, a farmer named Thai Ngoc claimed that a severe fever in 1973 permanently erased his ability to fall asleep, a story that prompted numerous international media investigations. But when modern chronobiologists subject these creams to polysomnography, the gold standard of clinical sleep measurement, a different reality emerges. The readings universally reveal hidden bursts of theta and delta waves. These individuals are experiencing sleep state misperception, where the brain achieves a light sleep state while the person believes they are fully awake. They are also slipping into undetectable microsleeps lasting fractions of a second. Absolute wakefulness is a historical myth. To ensure physiological survival, the brain will always force itself into microscopic slumber. The pressure to sleep is biological and relentless. As wakefulness continues, cellular energy consumption causes a byproduct called adenosine to accumulate in the brain. When adenosine binds to its receptors, it inhibits neural activity and creates an overwhelming biochemical drive for drowsiness. Once you enter deep, slow-wave sleep, the glymphatic system activates. The brain's glial cells actually shrink in size, allowing cerebrospinal fluid to rush through the tissue. This wave flushes out neurotoxic waste products like amyloid beta that build up during the day. This 1986 citation in the New England Journal of Medicine documents the fatal reality of preventing this process, a condition called Fatal Familial Insomnia, or FFI. It's a rare genetic prion disease that systematically destroys the thalamus, the brain's sensory relay station. The destruction of this region permanently locks the patient out of non-REM sleep. The resulting absolute sleep deprivation rapidly leads to severe dysautonomia, dementia, and death within 12 to 18 months. Sleep is an inescapable biological law. Eliminating it entirely is not a superpower, it is a fatal impossibility. If complete sleeplessness guarantees rapid physiological deterioration, it raises a critical question. How do certain people naturally sleep just 4 to 6 hours a night, wake up completely refreshed, and suffer no negative health consequences? While roughly 30% of adults claim to be short sleepers, the vast majority are simply chronically sleep-deprived. True genetic short sleepers, known as familial natural short sleepers, make up barely 1 to 3% of the global population. Thriving on limited rest depends on genetic mutations that increase the efficiency of their sleep cycles. Looking at this documentation from 2009, researchers discovered a specific point mutation in the DEC2 gene. This gene acts as a repressor in the molecular circadian clock. The mutation alters the transcription of target genes regulating wakefulness. As a result, individuals with this DEC2 mutation exhibit a naturally enhanced drive to stay awake and require significantly less rest to recover. These mutations grant a rare subset of humans a biological advantage, allowing them to bypass the standard 8-hour rule without any measurable cognitive or physical decline. To understand how they accomplish 8 hours of recovery in half the time, chronobiologists study a concept known as sleep sepsity. This chart compares standard sleep architecture to a DEC2 mutant. Normal sleepers spend significant time in lighter transitional phases. The optimized mutant brain skips this, condensing the same amount of deep and REM sleep into a tighter window for critical maintenance with zero wasted time. Further research reveals these genetic mutations carry distinct psychological traits. Short sleepers are highly energetic, are unusually optimistic, and highly resilient to stress, as well as jet lag. In an evolutionary context, true sleep success relies entirely on the mathematical efficiency of the neurological cleaning process. The implications of these genetics have triggered a global race. Pharmaceutical companies and military research agencies, such as DARPA's Continuous Assisted Performance Program, are heavily investing in synthesizing drugs that mimic the biochemical effects of these exact mutations. The goal is pharmacological mimicry, developing a pill that safely forces an average human brain to compress 8 hours of cellular recovery into 4 hours of hyperdense sleep. Doing so could solve critical endurance challenges in extreme environments. Modulating sleep efficiency genetically or chemically will be a deciding factor for deep space exploration, specifically managing astronaut sleep cycles and confinement during multi-year missions to Mars. But the most vital application is entirely medical. By understanding exactly how short sleepers clear brain toxins so rapidly, researchers are working to engineer breakthrough treatments capable of dissolving protein aggregations in patients with Alzheimer's, Parkinson's, and other severe dementias. While the human brain can never fully eliminate the biological need for sleep, decoding the genetics of short sleepers provides a pathway to master its efficiency, potentially extending the years of peak neurological health for the general population.